I actually am.
I'm just
It's only 15 minutes, right?
yeah, 15 minutes and then
15 plus 5. Well, 15 plus 5, so you'll get a 5-minute warning.
Sweet.
I'll give it a second. Just gonna.
This is. That's
Yeah,
your
I
mic.
tested this earlier. That was all right. We're ready.
It made it. It made it. You are.
Put it into
Oh,
mute.
you know
Yeah.
why? Well, you know why? I've got my slides set up. So that's fine.
Great. Have a good presentation.
Thank you.
So hi, I'm Brian Trammell, currently pseudo-academic. I am chairing the next session, which is on traffic engineering, for which we have 2 talks. First is invited talk from Nick Feemster, Princeton University, talking about why and how networks should run themselves. Why and how projectors should run themselves.
Here we go.
What?
There we
Yes.
go. Great. Where's the clicker here? Okay. Perfect. Great. So thank you for the opportunity to speak to the group. This is an invited talk, as Brian said, and a lot of this actually is forward-looking, future sort of vision. I based the talk on a bunch of past work that I'll refer to throughout. But there's basically a sort of one premise behind the talk, which is that it's been a lot of work in monitoring. There's been a network monitoring. There's been a lot of work in inferring properties of the network based on data that we collect with measurements, be it performance related, security related, etc. There has been a lot of work in control of networks, be it through protocols like netconf or similar, but software-based control of the so-called data plane. And the talk basically has one premise, which is like, hey, we've got a lot of building blocks. Should we start thinking about putting these together in certain ways to do more interesting and even more sophisticated things? And what kind of challenges arise from that? I'd like to think about network management in terms of this cycle where operators will get stuff out of the network, measurements from their switches, routers, et cetera. This might be anything from packet traces to NetFlow to SNMP. They then try to figure out what's going on, right? Inference, we'll say. And that could be things related to performance, security, failures, provisioning, anything you can imagine, and then do something about it, right? So react in some way. Okay, now, in many cases, these 3 orange boxes are separate activities. In some cases, we've seen some coupling of different aspects here. But I want to sort of talk about the past a little bit and then look forward to the future and point out that in all of these 3 areas, there have been very exciting developments that may enable closing this control loop in interesting ways. This, I think, by the way, relates a lot to some of the working groups here, both in the IETF and in the IRTF, Anima, some of the management working groups, MapRG and the IRTF, and so forth. So hopefully this will resonate, as well as NetConf as well, obviously. Okay. So I'll talk about each piece here. Let me start with inference. For each one of these 3, I'm going to talk about some past work, glimmers of hope, I would say, and I'm going to focus on some of my own past work with some of my students and postdocs. But for any one of these 3, there are 20 examples. Okay, so my point here is just to say, hey, there's some building blocks here. There's also a gap we need to cross to kind of close this loop. So in inference, there's a whole bunch of stuff that you can do, of course, once you've gathered data from the network. machine learning, or perhaps AI is the term I should be using now, but detection of attacks, what-if scenario evaluation, inference about performance or quality of experience, prediction for provisioning, troubleshooting, anomaly detection, the list goes on and on. I'm just going to mention two specific examples of things we've done in the past, and then where I think there's a gap to be bridged. So attack detection, this actually we've worked on for quite some time, looking at network properties to detect spam, to detect web-based malware, to use the routing, BGP routing messages and anomalies there to detect bulletproof web hosting, and one I'll talk a little bit more about, which is detecting and predicting the abuse of internet infrastructure by looking at anomalous patterns in DNS registration. So I'll mention just a couple of words on that just to give you some color, and then I'll sort of come back to the bigger picture. Okay, so this is some work by Shuang Hao, who was also a co-author on the work you heard this morning on TLS from Kevin. So typically what happens if there's an attack, be that malware or phishing or what have you, there's going to be a website that's set up. So if there's an email campaign or some other type of campaign, typically you want the user to click, right, so that they can go somewhere and buy something or enter their password or do something that you'd rather not have them do. Predating setting up the website, of course, you trace this way back. There's a DNS registration, a domain registration at some point, and it so happens that those domain registrations look funny, right? For one, there's basically they can be hosted in funny places. They can be registered through funny registrars. They can have strange things in the names themselves. They can have small edit distances to things that are previously on a blacklist or even to each other. So all those turn out to be pretty good features. Other things that turn out to be good features are a lot of times these shady websites for these types of activities are registered in huge batches, right? So it's not common that we, each of us would register thousands of domain names with very, very similar keywords in them, but that's a common thing that turns up in attacks. Okay, so it turns out that this is just one example of where you can use network data to infer that something bad is actually not even happening, that it's going to happen, right? So you can predict. That's pretty cool. Another one, what-if scenario evaluation. So this, by the way, was work by my former PhD student now at Google. This was implemented a while ago in the CDN provisioning use case scenario, and the idea was basically like, okay, if we deploy a new front end in our in the front end back end web architecture, or if we need to take down a front end for maintenance, what's that going to do to web search response time? Okay, so you can imagine that there's like a huge amount of steps that you would have to go through if you were going to do just closed form analysis on this, right? Because that has effects on round trip time, packet loss rate, et cetera. And the idea here was that, hey, if if you are a company like Google that has a lot of information about these lower level network properties and how they relate to much higher level quality of experience, things like search response time, then you can basically learn the relationship between those network properties and the higher level application quality of experience metrics and predict basically what's going to happen if you do something like move a front end or take it down for maintenance. So what if scenario evaluation. Since it's the IETF, I'll skip this slide. I'll just tell you that it basically works. Okay. Okay, so that's inference. Well, is that the end of the story? No. In a word, I will tell you that everything I showed you there was basically cheating. Okay, in a way, and the reason that it was cheating was that it's all offline. Okay, you've got lots and lots of traces. You collect them, you throw them into like huge clusters. You train your models for a long time. You run k-fold cross-validation, and you get some nice results for a graph like I just showed you. But we're a ways from doing this in a real-time closed loop. Okay. So good progress there, lots of work to go. Let me talk a little bit about control, right? So another thing that's happened over the last 5-10 years is through things like netconf, SDN, et cetera, there's been a lot of work in programmatic control over the configuration and even the forwarding behavior of these network devices. And also there's a lot of work going on down here in programmable data planes. Okay, so there's basically two things really going on, as I mentioned: programmable network-wide control and the ability to sort of customize how packets get forwarded in hardware in the switches themselves. Okay, so relates a lot to what's going on in netconf. Let me just give you one example of something that we worked on. So in a conventional IXP, as everybody knows, a bunch of ASs come together. They want to peer at this IXP. They exchange routes at the route server. To limit the pairwise BGP interconnections. And we basically said, oh, well, actually, what if you did something like take that conventional route server and turned it into like a controller of sorts, right? And had it talk directly to the switch. And this could be, we used in our work, we used OpenFlow 1.3, but this could be netconf or something else. The point here is that hey, you can actually do nifty things with control, right? If I've got a network-wide view over what's going on at my IXP, I could basically do things like have all of these ASs send more flexible, more fine-grained policies to that controller and do more flexible, interesting things. Let me just give you one example. What happened there? Okay. One of the things that we worked on, and I'm basically going to elide a lot of the details, but basically we looked at things like port-specific inbound traffic engineering and even port-specific peering, right? Okay, so cover your ears if you're worried about net neutrality. But basically, what we were looking at here is you might have an AS that would write a policy like this, right? That says, okay, if the traffic is destined for this particular port, send it out a particular port on the switch, and you can basically write that in a config, high-level config rule. You can put it in the switch, and the problem is, and where this gets, why this becomes a research paper is like that's all well and good, but it totally doesn't interact well with BGP, right? So we figured out ways to make this work nicely so that you can't send traffic out an output port that your neighbor hasn't advertised there. So there's a lot of interesting things going on there with how you couple programmable control with today's internet routing protocols, so you don't actually like break the internet. Okay, so there's a lot more going on in control. Obviously, that's one quick example, but just to say that again, on that piece of the picture, lots of interesting developments in, say, writing lots more flexible policies and extending what our network protocols can do. Finally, let me just say a few words about monitoring, right? So historically, this has been PCAP or NetFlow or Go Home. And we've been doing a lot of work on making telemetry more flexible. And I did see actually that there's a, I got a pointer to the draft itself, but I see there's a draft looking for adoption here this week that relates to in-band network telemetry. The idea here behind this work is, this is work of PhD student Arpit Gupta, is that there are a lot of analysis questions, like things that require getting measurements out of your network, right? But often, if it's packet capture or NetFlow or what have you, often you have too much or too little data. And could we better tailor the data that we're getting out of our switches and routers to the queries and the things that we really want to know? So one example that we looked at in this paper was DNS reflection, right? Okay, so for those of you who don't know about reflection, this is basically an attacker sends DNS queries with spoofed source IP addresses to resolvers, and those responses bigger than the queries go back to some victim. Well, let's say you wanted to detect that. You're interested in maybe getting information about from your network about DNS response traffic from a certain set of unique DNS resolvers directed at a single victim that exceeds some threshold. Okay, that's not something that you could typically ask for in in a BPF filter or by specifying a net flow config. But what we realized is that a lot of these types of queries map very well to query languages that already exist. For example, Spark, and the system that we built called Sonata is built on this language. So what I just said is basically represented here as a standard MapReduce query in Spark, right? So take your DNS queries, count the number of basically DNS servers that they're coming from that are directed towards each victim, take a threshold, and then do something with it, right? Something basically relates to the whole control loop that I talked about at the beginning. But basically, the idea here is collect data that's tailored towards the questions that you want to answer, right? Okay. And again, why is this research? Well, there's a lot of actually very tough questions there because most of these systems like Spark aren't really tailored towards getting like huge fire hoses of network traffic coming off of switches and routers into their cluster, right? So we got to do a lot of work to partition that query, put some of it in the hardware, figure out which parts of those map and reduce and distinct can actually go into the switches. And 10 years ago, the answer would have been none of them. But now, thanks to a lot of work in programmable hardware, we can actually map a lot of those primitives right down onto the switch and save some of the load coming up at that server box at the top. As I mentioned, there's interesting work going on not only in the research community, but also coming to the IETF on these network telemetry kinds of questions. Okay, so we've got all the pieces. Can we close the loop? As I mentioned, this is basic. We're part of the way there. Each one of these building blocks really is, we've got a ways to go. In inference, right, we're a long way from real-time, real-time inference, taking any of those problems that I mentioned at the beginning of the talk, right, anomaly detection, security, a long way from sort of putting that into a real-time control loop. Monitoring, right, we're pretty good at doing low-level network metrics and aggregates. Even the thing I showed you is pretty low-level. Okay, what about higher-level application characteristics and properties, like is the video stream rebuffering? Right? Or was there a change in the resolution? Or what's the join time across all of my clients, for example? And those are things that we are actively working on in our research. But again, those are all just sort of little steps in the building block. And I think basically, I think we should be thinking about one slide left, where we'd like to be. So closing the loop, there are interesting things that we could do in all three of these cases, ranging from getting real-time statistics on paths. So I think that telemetry draft that I just flashed up relates to that kind of question, to inferring properties up the stack, to even doing things on the security and privacy side, right? If we could close the loop in this way, we could do much better monitoring, right? We could gather only what's needed, which would help us both in the scalability aspects of things, but also in the privacy, right? A lot of times we don't want to gather things that we don't need to. The problem is we have to because of the way that our systems work today. So in summary, we've got building blocks in all three of these areas. There's a lot of things that we could do in making this kind of, closing this control loop in the way that I described. And I think there are challenges both in doing so and in figuring out what problems are most important to solve first. So I hope I've convinced you that we've made a lot of progress in all three of these areas, but there's a lot of work to do in this sort of network automation space. And there's a URL here to a website. We just had an NSF workshop on this as, I think there's quite an agenda going forward many years to come. So thank you.
Thank you very much. We have a couple of minutes left for questions if anyone would like to come up. Oh, cool. Then I get to ask the question.
Good.
So if you go back a couple of slides, there's where you identified the gaps. Which of these do you Right. So there's a real-time couple control gap. There's the lack of integrated access, and there's the low-level, high-level application. Which of these problems do you think are accidental and which are essential? Right. Like, so, I'm a monitoring person, so I look at the taking the low-level metrics and aggregates and turning them into QoE, and I'm like, okay, well, we have mappings that we can use there, but they're it's kind of black magic and it'll probably never work. Yeah, and it's getting harder because of encryption, exactly, right? So it's good for us, keeps us in business. But yes, yeah. But the I spend a little bit less time on the other two, so I'm more
Yeah.
optimistic about them. Is that just you're optimistic about what you don't know, or are these actually like so? The middle control plane thing, I think, is actually just something that standardization is a key way to fix that, and it's not like essential.
Yeah, I agree, and there's certainly work here in the IETF about sort of multi-domain control, and of these three, I probably work least in that area, even though I profess to know a lot about it. That never stops an academic, right? But no, I think there are hard problems in control. Certainly, people are working on them. I think the other areas, as you mentioned, are arguably a lot more difficult. And I think you hit on the problems in monitoring. I think inference also is very challenging. The quantities of data are large, and that's why a lot of these inference techniques work, because a lot of them rely on having tons and tons of data. The one I showed you about the what if scenario evaluation, like unimaginable amounts of data that take any deep learning problem, right? That works great for a paper. It works great for an offline analysis, but turning it into real-time control is another ball game. And that's not to say that it's hopeless. I think there's an area of machine learning research, active learning, right? So if you look at these sort of cost-sensitive optimizations in learning, that I think we will be able to make some progress in saying, like, hey, it's a lot cheaper to get packet headers than to get payloads, right? And cheaper might be performance cost. It might also be privacy cost, right? But once we put costs on these features, we can start to say, hey, I can do just as well with the headers, right, with this prediction problem than I can with all this other stuff. So I think that's where the interesting problems are there.
Thanks. So another like half a minute for each other question.
All right, I'll try to be quick. Thank you for the talk. I think it was really interesting. I'll definitely go read the work. I particularly liked that you honed in on in-band network telemetry. I think there's huge opportunities there. Really interesting. I have one really small comment.
Yeah.
Well, actually, I'll ask as a question rather than make a comment. What do you see as the difference between policy-based routing and traffic engineering?
Well, policy-based routing is a way to achieve traffic engineering, right? I mean, it's a particular implement. I mean, it seems to achieve that goal for many traffic engineering problems.
So
right?
I think we have a maybe a different definition of traffic engineering in the context of the IETF than what you're referring to. The ability to identify a flow and direct it somewhere.
Yeah.
We really think of, or most of us,
policy-based routing.
Policy-based
routing.
Sure. Traffic engineering is a little bit more than that.
Achieving an operational goal, for example. Or,
some of us, I'm not going to claim to represent everyone, but some of us also think that the ability to do some resource accounting and even some resource allocation, as in setting up queues, as an important attribute of traffic engineering.
I completely agree with you. Okay. Yeah.
And you're not doing that here, but this is still good stuff.
Someone could do it. Yeah, absolutely. No, I completely agree with your taxonomy. That's a very good point.
So we're about 3 minutes behind, Allison.
Just a little quick plug for a meeting. One of the network management research group is having a special meeting about machine learning that I think touches on a number of these topics, and it's taking advantage of the fact that we have a bunch of faculty in that space here in Montreal. So check on the schedule and join that later in the week.
Thursday afternoon, I think.
I think so, yeah.
All right. Thanks.
Ruby, coming up. And thank you very much, Nick. Next, we have Praveen Kumar talking about semi-oblivious traffic engineering with SMORE. So 15 plus 5, and I'll give you a 5-minute warning. Did it? Maybe. No. Let's see it. That's a MacBook Air, so it doesn't have HDMI. No, I don't have one of that. We did test it and it worked. Yeah, can we? Who's? It's IETF action at, right? Got no.
Oh, it was working.
Yeah, it was working. We tested it right before.
TV, or I can message.
Yeah, actually, just message real quick. It's definitely. It thinks it's. Is that Keynote or? It's Keynote. You know, it's Oh, you want to send it to me? Or we can run
Yeah,
offline?
yeah, try another.
Yeah. Yeah, but I think we're just gonna IETF at Primrose. Primrose, okay. So here, while you're doing that, let me have to make sure that this is going to work. Oh, yeah, that's not you. That's. Oh, wait. Okay, that.
Yes.
All right, nobody look at my to-do list.
Open Java. Open ATF.
That. Yeah. Now you know that works. Let me do this. We're loading it on mine. Yay. Downloading.
Can we plug in your machine while we do that?
Yeah. That worked.
I don't know. Wait.
Just my presence. All right. Yep, it's good. Yep. And there's your mic. Now.
Right. Sorry for the delay. Hi, I'm Praveen, and I'm going to present our recent work on semi-oblivious traffic engineering, which was presented at NSTI earlier this year. This is a joint work with collaborators at Cornell, CMU, Facebook, and USI Lugano. So in order to meet various competing objectives, operators of wide area networks use traffic engineering in order to steer traffic in desirable ways. And a good traffic engineering system must be able to achieve good performance in terms of high throughput and link utilization. It should also be robust to failures. Traffic in wide area networks have different latency requirements. For instance, low latency for customer traffic, while more relaxed requirements for bulk replication traffic. And finally, these traffic engineering systems should be simple enough so that it's easy to debug any issues that might arise in production. And traffic engineering systems must be able to achieve these competing objectives in the presence of various challenges. For instance, network capacity might be added based on anticipated demands. So this leads to highly non-uniform link capacities and unstructured topology, unlike data center topologies. Failures such as a link going down or a misbehaving router is quite common in such networks. Similarly, it is quite difficult to predict traffic matrices in advance. So a good traffic engineering system must be able to handle these failures and mispredictions in a graceful manner. A TE system must also be aware of any limitations imposed by the underlying hardware, as in, for example, the number of flow rules that can be installed on a router is limited. And finally, rapidly updating the routing state in response to changing demands can impose significant overheads on the routers. So let's look at a few examples of traffic engineering systems. Okay. Right. So the conventional approach to traffic engineering relies on traditional distributed systems such as traditional distributed protocols such as OSPF and ECMP in order to achieve good performance. For instance, by changing the link weight of this particular edge, an operator can steer the traffic over this other path. Now, this approach is easy to implement because it harnesses the capabilities of widely deployed conventional routing protocols. However, in order to achieve good performance, it is quite difficult in practice to change or to optimize the link weights. Further, these distributed protocols often do not work well when failures happen or during periods of reconvergence when link weights have been updated. So around 5 to 6 years back, enabled by software-defined networking, we started to see centralized solutions to traffic engineering. And SDN gives us global visibility and direct control over the network. So in principle, we should be able to implement the optimal routing scheme at any point in time. So for experts in this room, that would mean we formulate the routing as an optimization problem, say as a multi-commodity flow problem, and then solve it using a LP optimizer. Now, this should give optimal performance in theory, but in practice, it is difficult to get optimal performance because note that to actually achieve optimal performance, you'll have to solve the MCF instances quite frequently and update the routing state almost instantaneously. And this is limited because of various practical or operational constraints. For instance, let's look at the time required to solve an MCF instance. So this graph shows on the x-axis traffic matrices over a period of 1 week from Facebook's backbone network. And on the y-axis, we have time required to solve the MCF instance using an optimized LP solver. And we find that it takes around 30 to 40 seconds to solve each instance. So this imposes a fundamental lower bound on how quickly you can react to changes in demands. Similarly, there is no guarantee that the solution of an MCF instance at one point in time would be the same as the one that we solved just a few seconds back. And this leads to path churn. So for the same setup, this graph shows the number of paths, routing paths that we might need to add or remove in each iteration. And we see that we have to update 1,500 to 2,000 paths. And these updates need to be done in a consistent manner to avoid any forwarding loops, black holes, and to avoid any transient congestion. So this again imposes a significant overhead on the routers. So how did people actually build centralized TE systems? So to understand that, let's take a step back and see what a TE system fundamentally does. Essentially, it has to answer two questions. First is path selection. That is, it should tell us what are the set of paths to take from a source to a destination. And the second is, given these multiple paths from a source to a destination, how should we split traffic among these paths? And we'll call it rate adaptation. So it turns out that path selection is a slow and expensive process because we might need to update many geo-distributed routers for a single path update, but we can update the splitting ratios more frequently. So the key insight here is that we may not change the set of forwarding paths very frequently, but we can change the splitting ratio much frequently. So with this approach, path selection becomes tricky because since we have selected the path once, we are sort of committing to using these set of paths for a really long period of time. So it better be that these set of paths give us all the properties that we want, ranging from basic properties of connectivity to more efficient requirements, such as it should be able to handle failures and it should be able to handle misprediction in demands. So the key thesis of our work is that a static set of cleverly constructed paths can give us near optimal performance and very good level of robustness. Specifically, we highlight that the path selection algorithms should pick paths which have low stretch for good latency. It should select paths with high diversity so that the traffic engineering is robust to failures. And the third is the paths should be selected in a capacity-aware and globally optimized manner to have good load balancing. I'll explain what I mean by these two properties in the next slide. So suppose this topology in which we have all the links at 100 Gbps, except one link, which is a 10 Gbps link. And we'll use a shortest path-based approach, which is not aware of the capacity. And suppose A, B, and C want to send traffic to E. And in this case, since all the shortest paths go through this bottleneck link, we will have high link congestion. Now we can make this approach capacity aware by using something like constrained shortest path first, or CSPF. And using that, let's see what happens in this case, where we have made the topology more uniform. That let's say all the links are 100 Gbps, and A, B, and C want to send traffic to E. And all the demands are 100 Gbps again. So when A wants to send traffic, it will take the shortest available path and it will saturate the links along that path. So B will have to take a longer path and C will have to take an even longer path. This is clearly suboptimal because the paths were not selected in a globally optimized manner. So instead, if we knew all the source and destination pairs in the beginning and we could use those to select the paths, we could have come up with a much better set of paths. And we find that most commonly used path selection algorithms often do not meet the criteria for good path selection. For instance, shortest path-based approaches can give us low latency because they have low stretch, but they are often not diverse enough to be robust to failures, or they do not give us good load balancing properties. We can get good load balancing by using MCF, but we found that using MCF, the set of paths is very brittle to failures, and they often have higher latency. So in the past, people have looked at demand-oblivious schemes such as VLB or variant load balancing in order to achieve good performance. So let's look at oblivious routing in a little bit more detail. So VLB works by forwarding packets through random intermediate hops, and these random intermediate hops forward the packet to the final destination. So VLB has been shown to work really well for mesh-like topologies by providing good performance as well as robustness. However, wide area networks are not mesh-like. So even though VLB gives us good robustness, it will give us high latency because we will have to take really long paths, and this also contributes to higher congestion over many different links. So oblivious routing, which was proposed by Reka in 2008, generalizes VLB to non-mesh topologies. It does so by providing a hierarchy of intermediate hops instead of a single intermediate hop. More precisely, it computes a distribution over routing trees, and each routing tree is computed using an approximation algorithm which guarantees that the paths in each routing tree are not significantly longer than the shortest paths, so we get good latency. And in this iterative algorithm, we update the weight of each link based on its usage in the previous set of trees. So this means that we do not overutilize any particular link, leading to good load balancing. And also this leads to a more diverse set of trees, leading to more robustness. So this oblivious routing approach that was proposed in 2008 has good load balancing properties, and it has been shown that it is order log n competitive with MCF. That means no matter what demands arise in practice, we will always get the maximum congestion within a log n factor of what you would get with the optimal MCF-based scheme. So SMORE, which is our semi-oblivious traffic engineering system, proposes using oblivious routing for path selection, static path selection, and it combines with a dynamic rate adaptation that uses an LP to compute the splitting ratios. Now, previously people have shown that semi-oblivious routing is not much better than oblivious routing in the worst case, but these worst case scenarios do not occur common in practice. So what we look at in this paper is that how well does semi-oblivious routing perform in practice. So to evaluate SMORE, we conducted experiments with data from Facebook's backbone network. The backbone network consists of several geo-distributed data centers and points of presence across the globe. And we used the Yates traffic engineering system to perform high-fidelity simulations. So let's look at performance. So on the x-axis, we have time over half a week, and we will have columns for different traffic engineering systems. And on the y-axis, we'll have metrics for normalized throughput, normalized drop due to congestion, and maximum link utilization. So you find that the optimal approach based on MCF is able to route all the traffic, and the maximum link utilization varies between 40 to 65%, following a diurnal pattern. I'll not go through all of these approaches, but I'll just note that only CSPF, Oblivious, and SMORE are able to route all the traffic without dropping any traffic, and the performance with SMORE in terms of maximum link utilization remains closest to optimal. In fact, it remains within 16% of optimal on an average. Next, we performed a similar analysis for robustness, and in this experiment, for each of these traffic matrices, we failed one unique link in the topology and measured the performance. So again, optimal is able to reroute around these failures by rerouting traffic, and the failure loss, which is shown in blue, shows that optimal doesn't drop many packets. This similar trend is seen across all the traffic engineering systems as maximum link utilization goes up. And again, we find that SMORE is able to achieve good performance by rerouting all the traffic around failures and still keeping the maximum congestion close to optimal. Now, these experiments were done with a path budget of 4. That means we allowed only 4 paths to be used between any pair of nodes. So in the next set of experiments, we increased the path budget to up to 64, and we found that a few other traffic engineering systems are also able to achieve near optimal performance, but they need lot many paths between each pair of nodes to achieve the same level of performance as SMORE. Now, natural question to ask is whether these results are specific to Facebook's backbone network, or do they generalize over a large set of topologies and traffic matrices? So for this, we performed a large-scale experiment using data from the Internet Topology Zoo, and we created traffic matrices using the gravity model. So this graph shows the aggregate performance. Sorry about the fonts. On the x-axis, we have normalized capacity, where capacity is defined as the factor by which we had to scale up the traffic matrices before we saw any link congestion, as in before we saturated at least one link. And these are all normalized with respect to the optimal MCF-based approach, and we found that SMORE performs close to optimal. Similarly, we performed an experiment measuring the probability of achieving different levels of throughput or availability SLA, and we found that SMORE again performs quite well, and it is robust to failures. So to summarize, we found that path selection plays a crucial role in the performance and reliability of traffic engineering systems. SMORE, which combines oblivious routing for static path selection with dynamic rate adaptation, is able to meet the competing objectives of performance and reliability. So finally, we have made all the code for SMORE open source, so feel free to check it out. Thank you.
So we are running a bit over. We have time for one quick question. Run to the mics.
Hi, Rachi, UMass Amherst. So early on in the motivation slides, you were talking about how path diversity is the difference between using, say, k-shortest path plus multi-commodity flow versus SMORE. And I was wondering, like, bottleneck links themselves, how often are they actually a problem? And are these, like, what links are these in, say, a wide area network topology that you would say define bottlenecks, and then you would want to do something other than k-shortest path plus multi-commodity flow versus SMORE?
Right, good question. So with what we found is that the set of links which are normally congested when you use a shortest path-based approach, or that is k-shortest path plus MCF, is those which are central in the graph in some sense. So there are different notions of node centrality and link centrality. So these links are the ones which are central in the graph.
So you would think something like a transatlantic link or like.
Yes, it could be a transatlantic link. It could be links within the continent itself because they lie on many different shortest paths. So if you just take the entire, all the n squared nodes and you compute the shortest paths, then you'd find certain links which are there on most of these paths. So those are the ones that would be congested if you're using k shortest path plus MCF.
Thank you.
All right, thank you very much.
This is the last session for this amazing workshop, and we're going to start with Nikita talking about tap dance.
Hi, thanks, Roya. So I want to talk to you about some work we did on deploying a censorship circumvention system called TapDance. So one of the things that's interesting is that if you look at the population of internet users, a large number of them come from countries where their access to the internet is restricted. So this is a study that was done by Freedom House, and you can see that there's a very well-known example of China, who runs the Great Firewall of China and restricts access to its users to many different websites. But overall, if you include the partly free sites, the majority of internet users are facing some sort of censorship. Censorship is done by filtering people's access to the internet. There are many different approaches that are used. People manipulate DNS. People use BGP to null route certain things. Some of you might remember the Pakistan YouTube incident that resulted from that. People use deep packet inspection to look at content, though that's a little bit less popular now as more and more protocols are moving towards encrypted content and end-to-end encryption. I would say the kind of big workhorse of internet filtering is just simple packet filtering, where you deploy a packet filter at the border of your country that it filters things based on IP and port. So for example, last year I visited Shanghai. It was a very beautiful city, but when I went to my hotel and tried to connect to Twitter, the Great Firewall of China knows Twitter's IP address and blocks them. So any connection doesn't go through. Now, for those who know me, you know that I can't go without social media very long without getting twitchy. So what I did is I set up a proxy at my university. I set up a VPN that I connected through, and I was still able to use social media. So censorship is not foolproof. And in fact, this concept of deploying various kinds of proxies so users could connect to censored websites has been adopted by a large number of projects, Tor, Siphon, UltraSurf, etc. Unfortunately, this creates a bit of a cat and mouse game. What happens is that the censors now go after these proxies. They find where these proxies are located, and they block them. They simply add another block entry to this packet filtering list. Now, circumventors, of course, they work to deploy new proxies and to distribute them. But in the end, there's this race back and forth. The new proxies, new blocks. The advantage can be in the circumventor's pocket if they can make their proxies either harder to find, and there's work doing that, faster to deploy, so you can just bring them online more quickly, harder to block, and easier to get into the hands of real users. And so our project really works in this harder to block space. We want to make sure that even when these proxies are eventually found, it's hard for the censor to respond by blocking them. Now, our project is based on deploying a proxy within the infrastructure of some friendly internet service provider. And the system is called TapDance because what we use is we use a tap on the connection from a client that goes through a friendly ISP to some website that is not currently blocked by a censor. So, you know, this could be catpictures.com or anything like that that looks benign. The tap gets us a copy of all the traffic. And this is an important deployment architectural detail because we do not want to introduce an inline element here. That ends up being hard to deploy, but getting a mirror copy of the traffic that goes through some ISP was something that we were able to do with at least several ISPs. The way that tap dance works is you have a client make a TLS handshake to a not blocked server, to some reachable server, establishes a shared key, and then it sends an HTTP request over this TLS connection, including in it a special tag that is recognized by our tap dance proxy that sees a copy of this traffic. Because the request is incomplete, the real web server, the reachable web server, just waits for the completion of this request. At the same time, the station recognizes the tag and responds, sends a response in place of the real server. And from then on, communication keeps going in this way. The client sends messages ostensibly to the real server, but in fact sending requests to our proxy that then responds masquerading as a server. This is what an incomplete HTTP request looks like. So you can see here that it's incomplete because it's missing a second CRLF at the end of the message. If a web server receives this, it says, okay, I'm waiting for you to complete this HTTP message. This special Xignore header is constructed in such a way that when you encrypt it in your TLS connection, you get a certain message that has a particular format, that has something that we can recognize. In particular, it has two parts. One is a special key agreement component that gets turned into an elliptic curve point on something called an alligator curve. Using this elliptic curve point together with the station's private key, you can get a decryption key for the rest of the tag. And inside this rest of the tag, we have some shared secrets and also the client random so that we know that the decryption happened correctly. So what happens here is that if this message was sent by a tap dance client, we are able to successfully decrypt it and recover the key material that lets us take over the TLS connection. If it was sent by somebody else, then our decryption fails. And so we do this trial decryption on every single TLS connection. 99.9% of the time it fails, we ignore them. And when you have a tap dance client, we're now able to act as the other side of the TLS connection and pretend to be this reachable server while sending censored data. The other thing is that this tag, it looks completely random from the point of view of somebody who doesn't know the station private key, so it cannot be easily detected by the sensor. After we are able to take this tag and recover the key, we send a response here in step 5 that confirms that we have picked up the connection. And this response advances the server-side sequence number further than the real server actually sent. This causes a server, when the client sends new messages, to ignore any future messages that are sent, because it says this message has come with an acknowledgement number for something I have not sent yet. And TCP stacks, both by the RFC and according to our testing, just ignore those messages as long as the sender sequence number is within the window. So putting this together, you're now able to take over this TLS connection
and use it for, like I said, accessing sensor data. Now let me talk a little bit about our deployment. We worked with two ISPs, Merit, which is a regional research ISP in Michigan, and UC Boulder. And we deployed 4 total monitoring stations at their points of presence. Merit had 2 points of presence in Chicago and 1 in Detroit, whereas Colorado had 1 place where we were able to, let me see, add the station that sees all the traffic except for the science network. We then looked at what websites could be used as these target reachable sites in our deployment. So we did some scanning. We used data from Census to find all the websites that are in the right IP ranges that have an SSL capable web server that has a trusted certificate. We then filtered them to try to eliminate some that had really short timeouts or short TCP windows. That reduced, I forget, maybe about 20% of them. Then we also filtered things by whether they could actually talk to our client. And because we only implement a few of the TLS cipher suites, this actually brought them down to cuts out about another 2/3 of the websites. But in the end, we had about 900 reachable websites that we could use. And so what this means is that if you were to use IP blocking to block our deployment, you would have to block all these 900 websites. And this is what I mean by harder to block. You have to have a significant amount of collateral damage by instituting these blocks. In our trial, we deployed this to about 70,000 users by partnering with Siphon, a company that supplies software for Android that can be used in, uses a number of different censorship circumvention technologies. And just really quick numbers from our trial. So we were monitoring, our ports totaled up about 100 gigabits of traffic. At the peak, we saw about 60 gigabits of traffic, and so we were able to process this across 4 kind of mid-range servers, commodity servers. And our user traffic was several hundred of megabits. This is the traffic that went to presumably censored websites. This is the traffic that actual users wanted to connect. So, like I said, about 70,000 users. Several hundred megabits. So one thing that I want to mention at the end is that in addition to IP blocking, where the sensor would need to identify these 1,000 websites and block every single one of them, another approach that a sensor might be able to take, and probably most realistic at this point, is to note the fact that there's various tells that you can use to distinguish a tap dance client from a real web browser connecting to a real website. You know, a real web browser makes a DNS request, then opens up a bunch of connections to a bunch of different servers. It uses particular things in TLS negotiation that have a certain kind of look. It uses HTTP messages back and forth with various sizes, and all of these things create a certain pattern that can potentially identify a real web browser and might distinguish us. Some of the work that we're doing now is trying to make sure that we look more like a real web browser, so it's harder to distinguish us. So for example, in the client hello, we just switched to using the Chrome 62 or 64 version client hello, which is still used by, in our measurements, a few % of clients. One interesting thing that I want to point out is that a bunch of work that's going on in IETF actually makes our job easier. So the DNS requests, if they're sent over HTTPS or TLS, give less information for the sensor to be able to identify that something's going on. Encrypted SNI is not part of TLS 1.3, but there's discussions for it. Once again, make it harder to tell what's going on and makes it harder for the sensor to identify real traffic from sensor traffic. And so one of my takeaway points that I want to say is that a lot of these changes are based on and motivated by providing user privacy. But privacy has a secondary benefit that protocols that are designed for privacy are harder to censor because you cannot selectively tell what's going on. So I just want to close by thanking a large team of collaborators that we've had to make this project real. And want to say that we are in the process of working towards a sustained deployment rather than a trial. And we're always looking for new ISP partners. So if you happen to have a mirror port lying around that you're not doing anything with, come talk to me. Thank you.
Hi, Jay Vosberg, Canonical. So are these reachable end hosts that you're using as sort of the hidden proxies? Are they complicit to this scheme, or are they unaware that you're doing this?
They're unaware. We include a user agent with a URL that says that if for some reason if they find something in their logs and they want to talk to us, so they can go and find this out. But they're at this point they're not complicit.
So have you guys considered the possible legal liabilities for the ISP?
Yes, in fact, one of the partners that we have is Upturn, which is a nonprofit that looks at legal issues. And so they did some analysis of that. I can direct you to some of their findings. I mean, I'm not a lawyer, so I can't really tell you what the answer is.
And lastly, you said you had 900 of these reachable sites. Is that list public? I presume not.
That list is not public, no. Though, I mean, you could generate it yourself using our methodology.
Okay, thank you.
Hello, Frode Kielen from Telenor. We are one of the ISPs which is operating in many countries that are considered to be very limited, have limited connectivity. And we looked into this, it was not any formal analysis. And what we saw is so easy to detect that an operator and ISP in these countries are running this, providing this by testing. So, and these ISPs are very strictly regulated by the countries. So when it's so easy to detect by testing, much of this falls apart. These ISPs have a lot of investment in buying licenses to operate, and when they are in breach of the licenses and then can easily be discovered, that is a big issue for the deployment and for in these regions where this is needed.
I'm not sure if I fully understood your question. I'm sorry, but this is definitely not something that, like, I think every single ISP can deploy. There's definitely different reasons why different ISPs may not be able to do this. So we're never thought about, doing kind of a global deployment. So the ISPs that we have worked with were comfortable doing this, though they also had some initial concerns that we overcome.
Yeah, I was in a meeting where we tried to recruit ISPs. But the thing is, it is easy to test this presence of this, isn't it?
It is possible to detect the presence of this. Yes, that's right.
Is it easy or difficult?
It's well, I mean, it's I'm not sure I can qualify it as easy as difficult, but let me just explain about the detectability. The easiest way to detect it is to get a copy of our, be one of those users who uses our Siphon client and see what ISP you're connecting to. Well, like answers to the last question, we don't have a public list of destinations and ISPs. Well, this is public that are being participated. So it's not trivial to figure out which ISPs are using this, but the project is not, one of our goals for this project is not to keep the identity of these ISPs secret. The goal is to operate even these ISPs are known.
Yeah, but your goal to support bypassing of censoring in different countries. So it's pretty easy if you connect it to different ISPs and you see that you can bypass the censoring.
I see. Right.
So
It depends on the ISP. There's a line of work that tries to figure out how easy it is to get to one of these not blocked websites by changing your routing rules, and it's a little bit. I don't have time to really summarize it in this time, but I can talk to you more offline about it. I can show you a few papers.
It's a nice work. Thank you. But
yeah, thank you.
There's some challenges for us.
Okay. No, thank you very much for that point.
Hi, David McGrew from Cisco. So this is cool work, but I've got a couple of questions.
Yeah.
So on the detection method, you didn't list TCP, but if I understand the presentation correctly, you're using some TCP hack of sending an acknowledgement number that's out of window.
I mean, yeah, it's something that basically it happens automatically on the client because we send a message, we inject a message from the tap dance station to the client, and then the client will automatically respond with a different acknowledgement number.
So wouldn't the non-standard use of TCP be detectable?
But the non-standard part of it is only visible on the, just excuse me for 1 second. If you look at this end of the slide, it is non-standard. If you look at this end of the slide, everything looks as if it should be because you get a message that's acknowledging it, and now you get a new message, and then you acknowledge this message in your sequence. Here, you get, at the server, the decoy server, you get messages that are out of order from TCP. And so that part is non-standard. But the sensor's observation point is over here.
Got it. Thank you.
I'm sorry, we don't have more time for,
Okay.
but Nikita is going to be around after the session and hopefully can answer to more questions. The next talk is going to be by Rishi, and it's about discrimination of Tor users.
Hi, everybody. Thanks for staying. I'm Rachi. I'm a PhD student at UMass Amherst. And today I'm going to be talking about the nature and dynamics of Tor exit blocking. This work was done in collaboration with folks at UMass, Stony Brook, UC Berkeley, and ICSI. So as folks might be aware, the Tor network allows its users a way to communicate with content on the internet anonymously. So as an example, here I have Alice, who wants to browse the internet anonymously. So when I say anonymous, she does not want to give away her IP address as she accesses content. She's using the Tor network to do so. So her traffic reaches the Tor network, and from there it makes it on the right-hand side towards servers that are hosting popular content. Now, a problem in this setting that a lot of content providers face is that when Alice's traffic reaches from the Tor network, they're not entirely sure if this traffic is malicious or benign. And as a result of this, Tor users have started to face discrimination or differentiation from content providers. What this means is, at times, Tor users see a variety of captchas that they need to solve to be able to get to the content they're looking for. And sometimes it can be as bad as being outright denied access to the content. And I think this is a problem. It's a problem for two reasons. The first is there are people like journalists and activists and people behind state-level censors who are using the Tor network to get to content they can't get to otherwise. The other reason is, which we think about lesser, a recent report found that Tor users are just as likely to make purchases on, say, revenue-generating websites as non-Tor users. So basically, both ends on this, both parties in this thing are losing out. The Tor networks are not able to get to content they want to get to, and revenue-generating websites could potentially lose money here. So this is sort of the backdrop in which we place the work that I'm going to be talking about today. Just to sort of set the stage here, I'm going to walk us through what sort of interaction really happens when a benign Tor user faces discrimination while accessing content. So I know this figure is kind of crowded, but I'm going to direct your attention to pieces of it. On the left side, I've got two users, user 1 and user 2. User 1 is a benign Tor user. User 2 is malicious. And both of these users want to access some popular content that's hosted on server 1, server 2, and server 3, and they want to do this anonymously. So as they want to do this anonymously, in the middle, I have a simplified representation of what the Tor network looks like. There is an entry relay, there's a middle relay, and there's an exit relay with a certain IP address. As folks know, that servers on the internet face a lot of abusive traffic. So all of these servers are subscribing to some form of threat intelligence, which is basically serving as a line of defense against, say, attacks or whatever malicious traffic they receive. This threat intelligence could be something homegrown. It could be something which is like a central repository that everyone has access to. So these are the different parts of the equation here. And as an illustration, our malicious user, user 2, is trying to attack server 1. And they do it using Tor. So user 2's traffic makes it to the Tor network, egresses the Tor network, reaches server 1. Server 1 realizes this is an attack. And as a server that's under attack, there's a number of things you could do. For instance, server 1 says, this is an attack. I'm going to tell my threat intelligence provider, hey guys, this IP address 1.2.3.4 is bad. That's one scenario. Now user 2 tries to attack server 3. Server 3 realizes this is an attack. And another scenario, server 2 is going to send an email, an abuse complaint to the whois contact they can find for this IP address. And folks in this audience are probably quite familiar with how abuse emails work. You find the abuse contact of the autonomous system that's announcing this prefix. You send an email saying, I'm receiving bad traffic from this IP, please stop doing so. And now, after all of this has happened, our benign user that just wants to get their cat videos accesses content on server 2, and they get blocked because it turns out server 2 is subscribing to the same form of threat intelligence that server 1 and server 3 were sort of contributing to. This is one of the ways in which a completely benign Tor user is facing differential treatment on the internet, and this is a problem. Another way this could have happened was if this threat intelligence system I have on the right side here was simply just crawling the consensus, the Tor consensus, and listing all known exit IPs as a blacklist or something. So what we wanted to do was to understand exactly what happens in these scenarios and which of these scenarios really plays out in the wild. And how would one go about doing something like this? Is that we take this complex interaction and we try to figure out where can we place our vantage points to understand these scenarios better. So what if I could simulate being a benign Tor user and at scale figure out what is the sort of differentiation that Tor users face when they access content? What if I could introduce exit relays of my own, and then I could see what properties of these exit relays can I change, and then sort of realize what kind of treatment I get on the internet. What if I could get access to abuse complaints that exit operators get, right? Then I could use that as a proxy to understanding this is the sort of abusive traffic that people face from Tor, and then that's something that we could, that's a problem, a concrete problem we could work on. And finally, if I could get access to something that's commercially deployed threat intelligence, I could figure out how do Tor IPs sort of harness this bad reputation? How does it happen over time? What can we do in this scenario to fix the problem? So this is exactly what we do. These are the 4 key questions we answer by introducing vantage points in this complex ecosystem. So I'm going to quickly sort of highlight what our methodologies are for answering this question and what do we learn from this. So first, I'm going to simulate being a benign Tor user and at scale access popular content on the internet and see what sort of discrimination do I face from servers. So to do this, we designed an automated crawler which crawled Alexa top 500 websites. And our crawler was capable of sort of interacting with these websites by trying to log in, by trying to search and things like that. Since we were doing this from Tor, you can see on this side, there are some example screenshots of what we got back as a benign Tor user. We were denied access. The crawler was asked to sort of solve a lot of captchas and so on. Now at scale, how often does this happen? So we found that 20% of Alexa 500 websites discriminate against Tor users at the front page level itself. So you access, say, the home page and you see some form of discrimination. This discrimination ranges from, say, solving captchas. It could be as bad as like being denied access. Now, of the websites that did not do this on the front page, about 7% or so discriminate if you try to log into these websites as a Tor user. And another 3% or so will discriminate if you try to do a search, exercise a search functionality on these websites as a Tor user. So this basically says that we did not understand this as well before. This discrimination is clearly it's quite bad at this point for benign Tor users. The next step that I want to talk about is, if folks remember, I said that Tor has exit relays of its own. How about I launch some of ours that we can sort of change the properties of and see how they impact the treatment that people get then once they use these exit relays. So we did that. We launched 10 exit relays of our own with different sort of properties. Some of these, so when I say properties, I mean what sort of uplink do these relays have to the internet? There was small, medium, and large exit relays depending on how much bandwidth they were allowed to use. And then there were, the relays have something called an exit policy, which is basically what sort of traffic is this exit relay okay with egressing. So what port numbers is it, would it send traffic to and so on. So that's basically an exit relay's exit policy. And we varied that from default, which is a default policy Tor allows for its exit relays, and reduced, which is a much more conservative policy, which does not allow a lot of variety of traffic. And the reason this is sort of important is we thought that if we could make the exit policy more constrained or more conservative, maybe traffic that comes from these relays gets treated better from servers hosting content. So that's one of the hypotheses we wanted to test here. So just to sort of put this at the back of your mind, we did this, and then we harnessed the data from these relays, and I'll show you what we learned there. So abuse complaints that exit relay operators get, we wanted to analyze these and use them as a proxy to figure out what abusive traffic comes from Tor. So we did that. The reason it's important to do something like this is that in general, if you do not have server-side coordination, it's sort of hard to get access to something that lets you decide what fraction or how much of the traffic is abusive from, say, the Tor network or other endpoints. So by using these abuse complaints that exit operators received over a period of however many, like I think 3. So the dates are from 2010 to 2016. So for that period of time, we looked at the abuse complaints that exit relay operators got, and these are 25 exit relays, 10 of which are our own, and the other 15 are the ones that had been running in the Tor network for a while. And then we sort of did automatic clustering on them, did some analyze them using regular expressions, and we basically found that a large majority of these abuse complaints are DMCA related. I'm guessing this does not surprise people in this audience. There were a lot of DMCA complaints related to BitTorrent traffic from Tor. And we know that these complaints tend not to be very high fidelity in nature. So we sort of did not analyze them further. And we looked at the non-DMCA complaints that people receive, that exit relay operators receive. And of these, 38% were about botnets and compromised machines. So we're trying to understand, this is basically the kind of abusive traffic that you would see coming from Tor. And there's like a distribution of what are the types of complaints we saw. The important thing here to note is there was sort of no correlation between what exit policy the relay had and how many complaints did it get. So the hypothesis we were trying to figure out that can we sort of fix this problem by changing how conservative the exit policy of the relay is. And turns out that does not seem to be the case in this analysis. Switching gears a little bit, I'm finally going to get to the last part of this equation, which is commercial threat intelligence, and we want to understand how does commercial threat intelligence treat Tor exit IPs and what happens over time. So for this purpose, we were given access to Facebook's threat exchange data, which basically is an aggregation of threat intel information from a number of companies. It consisted of over 100 blacklist or feeds consisting of like these IP addresses have done something bad in the past. And using this threat intelligence information, we looked at how do exit IPs harness bad reputation over time, how soon do they get blacklisted, and so on. And we found that, so I'm going to show you this plot, and like I think the point I'm trying to make here will become evident. So on the x-axis here, I've got time in hours, and y-axis is sort of the cumulative distribution function. And that spike at 0 is basically saying that all of these IP addresses got blacklisted on this particular feed that I'm talking about in the threat intelligence data as soon as these relays came up online. So basically, this is like blacklisting of Tor IP addresses as a matter of policy. These relays hadn't really been around to actually do some damage at that point, but they got blacklisted almost immediately. And we refer to this as proactive blacklisting of Tor relays. On the other hand, if the blacklisting takes its time after the relays are born in the Tor network, we try to think that this might be in response to abusive traffic that's coming from these relays. Sadly, 7% of commercial blacklists that we analyzed, they block Tor proactively, or it's a matter of policy for blocking Tor exit IP addresses. This graph is kind of messy. So on the x-axis, I have got time, and that bar says that this relay came online at that point of time, and the brown line is sort of showing this relay was alive in the Tor network. All the other colors are basically trying to show this blacklist blacklisted this relay in this span of time. So it's interesting to note that as soon as a relay comes up online, there are blacklists that enlist them, and these are our own relays. So we were able to like take them up, take them online and offline as we wanted. As soon as so once the relay is gone, it took the very proactive feeds a few days to sort of purge the IP off themselves. Then again, we brought the relay up online, and it got enlisted on these blacklists very rapidly. And these are some blacklists they had like a short-term ban, which makes us feel like this was done in response of abuse. After the abuse ended, the blacklist de-enlisted the Tor IP address. So there's both kinds of blacklists that you can see, some that are more reactive in nature and some that are more proactive. And like I mentioned, we did not find a correlation between how a relay gets blacklisted and its exit policy. So that hypothesis we began with did not really, we found an answer to it, and it seems like a conservative exit policy is not really the solution. So I want to conclude and then sort of think about, get people's opinion on how we could do something better here. So the first thing that I want to highlight is blacklisting of Tor IP addresses ends up being a matter of policy in a lot of cases. We find that a lot of commercial blacklists are crawling Tor and enlisting the exit IP addresses. So there's, before we could see some evidence of abuse coming from these IP addresses, they got listed on the blacklists. And there's worse than what we understood before. There's a rejection of Tor by websites for like search and login functionality as well. So I think to me the key interesting points here are the sort of fate sharing dynamics in Tor. So where Tor exit IPs, even though not all users are malicious, a bunch of them end up sharing fate because the exit IP is common for the traffic that's coming out of the network. And I do not think IP blacklisting sort of does a good job, because a lot of benign Tor users end up sharing fate with these bad guys. So if folks have opinions on this, it'd be great to know. Thank you.
Thank you for your insight.
Hi, Philip Prindeville. I contribute to Spam Assassin, Mine to Fang, mod security on Apache and so forth. And I'm just wondering if the web servers can detect bad entries and decide to blacklist you, why don't you just apply the same tests on the ingress side of your network so that those requests never make it out the other side?
So making logging any kind of information about who is sending bad traffic or sending any kind of traffic is sort of different from what the goal of the Tor anonymity.
I'm not saying logging it. I'm saying filtering it.
So are you saying that on the entry relay, I keep track of which requests are malicious?
No, you don't need to keep track of anything. You see the malicious request and you block it. End of story.
Right. So that would involve changing the relay software itself, right? Like I would need to run some sort of fingerprinting there, which says, okay, this looks like attack traffic.
Right.
First, I do think there are some efforts that are similar but not quite the same that are going on. And that's on the egress end of the network, not really on the ingress end. And second, I do think that it makes people a little nervous to have any kind of information being logged on Tor exit relays because it's a slippery slope.
Right, but if you're going to let bad entries through your infrastructure, you're going to be spanked for it, and
Right.
you shouldn't be surprised.
That is true, but aside from the fact that there's malicious traffic, there's also benign traffic, and the point that I was hoping to make here was if there are these long-term bans for IPs that at some point in the past have exited malicious traffic, I think that's bad whether it's Tor or not.
Right.
Right. So like I do think that's what you're saying, that there should be something within the network that tries to detect if traffic is malicious or not. And I think there are some efforts in that direction towards the egress end of the network, not the ingress. But at the same time, like long-term blacklisting does not seem to be a solution in general anyway.
Okay. Well, the mod security rules that Apache uses, they're very portable. You could probably do some post-processing and make them work with your infrastructure as well, so that you're using the same triage rules for bad traffic as most of those sites that you are seeing.
Are the mod security rules public?
Yes.
Okay, that would be a great resource. Thanks for pointing that out.
I just wanted to point out that you can only do filtering by IP address at the ingress level if you were doing any kind of filtering at Tor, because the ingress level does not see what kind of traffic is happening. Is that what you were talking about? Just
Yes.
IP based?
Yeah, I was talking about looking at the HTTP requests themselves.
You can't do that, right?
Yeah.
So you can only filter by IP because the ingress
Is
of the Tor
encapsulated.
network does not see the contents of the traffic. It just sees somebody connecting to the Tor network and then relays encrypted traffic over to the egress.
Okay. Like I said before, if you're not gonna do any sort of admission control on the ingress to your network, then yeah, you're mixing the bad with the good, and you're going to be spanked appropriately.
Right, but that's kind of a fundamental design trade-off for anonymous communication, right? Because if you could separate, if you knew what people were doing and where they were going, they wouldn't be anonymous for you.
So at the egress end, so if I think that it is possible to do something at the egress end.
You could do filtering on egress,
Right.
unless, though, hopefully not. Hopefully people are actually using end-to-end encrypted protocols. So the egress filtering, if you use HTTPS or start TLS or anything like that, then also
that
the
wouldn't
egress
work.
filtering.
But like if it's say like 38% of the abuse traffic, or the complaints were say about botnet traffic and so on. So if this is like on a particular port or something that looks like a port scan, I think that kind of traffic can possibly be filtered at the
Right,
egress.
and there's some policies reject various kind of ports as well. So.
Quick thought on that. Just because it's encrypted doesn't mean you can't tell that it's attack traffic, right? One can analyze properties of the encrypted traffic too, and maybe make blocking decisions, or no.
Yeah, that's an interesting question.
There are fingerprinting attacks that happen which are like attacks on the traffic correlation and things like that.
Yeah, that's kind of what I'm getting at. Is like you sort of like throw up your hands and say it's encrypted, we can't tell anything. But that's actually not the case. I mean, we know all kinds of attacks against encrypted traffic. We could maybe use them for good in this case.
Existing filtering tools do not filter based on that. So, but you're right.
Thanks. I think thanks. The session is ended, and I leave it to Sharon to end the session. Thank you, Rachel.
All right, so we finished the talk portion of the day, sadly for me, because I'm so excited about all of this. So thank you, everyone, for attending through this part. Just so you know, we had 44 submissions to this workshop, and we've accepted, right now, I think we have 18 posters in the other room. So if you go to the program page, you can see the list of posters. They're all in there. The presenters will be here. So this is another opportunity to kind of connect directly with researchers and IETFers. I hope people will take this chance. Everyone can join us in the next room. We're sort of scheduled at like 6:40 to end this, but it's very fluid. So please, everyone is welcome to join us in Agora room. Thanks again. It was a real pleasure to hang out with you guys now, and I'll see you in there. Thank you.
Well, yeah, there's. I think there's. Well, right. So that's not something that's internet level. That being said, there's different ways people try to qualify that. So the one-sided way